Welcome back to Missouri Caves and Speleology. I'm Toby Dogweiler. Our topic for this segment is karst landforms. I think even if one doesn't know anything about karst geology, you'd probably be familiar with the basic landscape elements or landforms that comprise karst that are important. First of all, caves. That's why we're here. That's probably what drew you to this course, was caves in the title. But we also have springs and sinkholes, sinking streams, disappearing streams, all these different features that people are familiar with, especially if you live in the 20% or so of the continental U.S. that has karst topography, shown in red on this map. So these are generally areas that have carbonate bedrock, carbonates being limestone or dolostone, that are capable of hosting and developing the karst features like caves and sinkholes that we associate with karst topography. You can see big areas like Florida, big areas in the Midwest, including that big red splotch in southern Missouri that is one of the densest areas of cave development in the world. These karst landscapes or topographies are comprised of lots of different landforms. In this image, you can see the caves, different levels in it, sinking streams where the water goes from the ground surface, maybe falls down a waterfall or just a steep passage, sometimes not so steep, and enters into a cave system, flows through, and comes out at a spring. We also have elements like the bedrock here, which has been weathered, maybe even the soil stripped away. And of course, people live and work on this. So you can see in the upper corner there, an agricultural area where there's some farming occurring. We could also put cities. The city of Springfield, where Missouri State University is an urban area that's on top of a karst aquifer, a karst topography. And so that's an important issue to consider as Springfield thinks about how to plan and develop its growth. This is another one of these schematic diagrams that show a fairly generic karst landscape with many of our landforms we're going to discuss today. So I'm going to refer to this diagram as we go through these different elements, just to point out where the landforms that we're talking about can occur on these landscapes. The red arrow shows an area of the landscape that may have thin to no soils on it, and these soils or that area of the landscape, then the bedrock is exposed, and we can see what's called the epikarst. Epikarst is sort of like, it's a term that refers sort of like the epidermis, the upper part of the top part of your skin. This is the outermost part of the karst system. So here we have the limestone where it first comes in contact with rainwater, which is moving down through a soil, or maybe even directly onto that limestone if no soil is present, and is being attacked and dissolved by that rainwater. Limestone, like all bedrock, tends to have natural fractures in it. And these fractures, as you can see in this picture, are often at roughly right angles to one another. Those are the easiest pathways for the water to follow. So the water is going to attack those and enlarge those and create this blocky appearance that we see in this photo. This is more of a cross-sectional view of a similar thing, and it shows us, you can see the corn stalks at the top with a thin soil, and then underneath that, the very upper part of the limestone there is heavily weathered. In some places, the soil sort of fingers down into the places where the limestone's been completely dissolved away. And then as you get further down in the bedrock, it's more intact, less weathered as we get further away from the surface. But you'll start to get small little conduits and things like that that eventually could develop into bigger caves. This is another example of some epikarst. In this case, it's an example from Florida, just where you have relatively young limestones that have formed relatively recently. We're talking recently in the geologic past, so many, many years ago in terms of human time scales. But it's been exposed at the surface in Florida and just sort of weathered away. Big parts, and what you're seeing are the remnants, the parts of that upper part of the limestone that just haven't been weathered away yet, and you get this really rough, jagged landscape. Back to our generic diagram here of a karst landscape, and the next arrow points out where some sinkholes could occur. And we're going to look at some different parts of this landscape where sinkholes are, but in this one it's just some isolated sinkholes now and then. Of course, sinkholes can be big hazards on the landscape. This is an example where this particular farmer, he had driven his tractor up this grass waterways his whole life, back and forth across that exact part of his farm. His father worked this farm before him, but one day he's driving along there and sinkhole collapses right underneath. So this sinkhole had probably been forming underneath the surface and sort of undermined the surface, and the weight of the tractor just finally collapsed it in. So these sinkholes can form relatively quickly, sometimes instantaneously, overnight. This is another one near where we are here in Springfield, south of us, at a resort down in Branson, where a big sinkhole formed on a golf course a couple of years ago. This actually made national news, and this happened similarly. The sinkhole formed from the bottom up, undermined the surface, and then just all of a sudden collapsed one day. So these can be big issues. This diagram is just a cartoon, and if you pay attention to the layer that's outlined in red, that's sort of a reference layer. Initially you have a fairly intact limestone with a thin soil over top of it. Through time that epikarst develops, and some pathways get enlarged and the soil starts to seep down as those pathways in the limestone get enlarged. As we move to the third part of the diagram, we've got a lot of the upper part of the limestone's now been dissolved away, filled in with soil. That process continues through step 4. And then you'll notice at the bottom, in the bottom right of that diagram, a conduit is forming that's connecting to maybe a larger cave system below that's able to start to move the soil away, and eventually through time, as that soil just gets piped away through the cave system that's underneath of this, you get a sinkhole developed. So in this case, the sinkhole developed was gradual and slow through time. In other cases, that soil layer at the top maybe has some cohesiveness and is able to stand up on its own as the soil underneath of it is eroded away until it no longer can support itself and it just collapses. Another type of sinkhole is one where we're actually having a lot of water that's moving into the subsurface. Sometimes these pipes can become clogged and will form a pond. If you look closely in this picture, you'll see some people swimming in it. So this is a pretty large sinkhole. It's pretty well defined in its sides, and it's holding a lot of water. Now these can be very dynamic. They can hold water one day, and then the plug that's choking that conduit that's draining the sinkhole can suddenly loosen up, and the drain can clear and all that water can wash away, and then it can replug and fill back up. And I think we've seen in some places, as we've studied the sediments that deposit in these sinkholes, that this happens repeatedly through time. Another example of a sinkhole pond, in this case on a farm. And then sometimes, as we show in the area that's under the red arrow here, we can have really densely populated areas of sinkholes. This is an example from New Zealand of a sinkhole plain, and you can see all the different sinkholes across this area, pretty densely populated. They're dark because usually they're filled with trees or something like that, because they're a little lower than the rest of the landscape and aren't being farmed or plowed or other things, so the trees can continue to grow there. But you'll notice if you look closely at the sinkholes in this picture that they're not necessarily randomly dispersed. They sort of show up in lines. And those lines are along the fractures. If you remember back to some of our earlier photos of the epikarst, we saw that as the limestone erodes, as it dissolves away, that the fractures in the limestone preferentially dissolve and form those well-defined lines between different blocks. Well, in this case, those are the preferred areas of sinkhole formation, and where we have two fractures that cross at right angles, we have potentially a really good spot for sinkhole development. So you can actually map those fractures across the landscape by sinkhole occurrence in some cases, even if soils are covering up the bedrock and you can't see the fractures directly. The sinkholes tell you where they're at. Moving to a different part of the system, we have the area where water enters the system. So somewhere the water has to get into the cave system. In this case, it might be a sinkhole, which is one of the earlier pictures we looked at, or in this case, a sinking stream or a disappearing stream. Here's a place where we have what is a stream bed, but you can see in the middle of the stream bed is an entrance that's filled with sticks and rocks and branches. During heavy rains, water will start to fill this stream, and that water will just flow down into the cave system through this what we might call a swallet that allows water into the cave system. Here's another one where you actually have water flowing into the cave system itself. So the stream just ends right there at that wall where the person is sitting, and water flows underground into the cave system. This is an example from Missouri, central Missouri. This is a stream that during dry weather doesn't have any water in it, but you can see it's pretty good size. There's somebody standing there for scale. Lots of rocks in there, not much vegetation. The lack of vegetation suggests that this stream does flow frequently enough that it keeps the weeds from developing and growing in there. And that's true. So anytime you get a big thunderstorm or a couple of days of rain, this stream fills up and then drains into a cave system. And in this case, it's not just one point. In this stream, there's multiple swallets, and when there's a little bit of water, the first swallet is able to swallow all the water and take it into the cave system. If there's a lot of flow through the stream, some of the water will go down that swallet, but not all of it's able to, and it'll flow to the next one, and there's a progressive sequence of these. In really, really large storms, some of the water makes it all the way through this segment of the stream without being able to get into the cave system. This is another example of water flowing into what is a pretty spectacular looking cave entrance and limestone outcrop. So the stream in this case just flows right underground. If we look at the other end of the system are the springs. Of course, we've all heard about springs and seen springs and probably experienced them. One of the myths out there is that spring water is somehow purer and better, and a lot of bottled water has spring in its name to try to convey that sense of purity. In reality, and we'll talk about this in other segments, water through karst systems can move very quickly without much chance to be filtered or for contaminants to be dispersed or attenuated. So spring water, ironically, is the last water I'd want to drink straight out of the ground. But the springs are at the downstream end of the system. We've got two red arrows there. Sometimes the springs occur kind of high up on the side of a cliff. Other times they seep up out of the ground. This first example is some springs in Idaho. And you can see this is called Thousand Springs. There's just a bunch of different little springs all in the same area where water's leaving the cave system and coming back out into a surface stream. This is an example from central Missouri. A few pictures ago, we looked at a great big stream bed that had a series of swallets in it but was dry at the time we looked at it. This is the downstream end of that system. At the other end, the water's going in. At this end, the water comes out at the spring here. The equipment there with the camouflage on the side is actually some equipment that's used to monitor the water quality and the amount of water that's discharging from this cave system. This is the Devil's Icebox cave system, which is in Rockbridge State Park in Boone County, Missouri, up by Columbia. This is one of those springs that comes more up out of the ground rather than coming out of the side of a cliff or something like that. This is one of the springs that drains Mammoth Cave in central Kentucky, one of the largest cave system in the world. There's actually more than one spring, but this is one of the larger ones, more famous ones. And here the water's being fed from a throat that comes straight up out of the ground from depth. And on a day like today, it just sort of gently comes up and it looks like a flat pool. If you come back to this spot when there's been a big flood, the water boils up out of here very violently. This is another cave mouth. This was the photo on the intro to this segment. This is actually a spring. This is where the cave just ends at the surface and drains back into a surface stream. let's look at the inside of caves. Caves are, of course, one of the most intriguing and interesting parts of the karst landscape, the landform that most people are familiar with and people often are interested in exploring. So we'll look at some of the features that define a cave itself. First of all are the entrances. This is a photo of actually me standing in an entrance to a cave in south central Missouri. You can see it's a pretty big passageway. This is looking back out of a cave entrance, another cave in central Missouri. I threw this one in there just because it's kind of a pretty picture that shows you emerging from the dark underground, the stream gently leaving the cave and emerging back to the green surface. So those are some of the entrances to the cave. One of the things that define many of Missouri's caves are red mud, what J. Harlan Bretz, our friend over here, called the red unctuous clay. And you can see me and another cave scientist standing in this stream. We're actually looking for some cave critters there, but what I want to point out in this picture is that red mud that's filling in the bedrock that makes up the actual cave, and the stream's running through that red clay. This is what we would call a Vados passage in a cave, and a Vados is a fancy word for this is a passage where water's trying to get down to the water table. So these passages, because water's trying to get down vertically through the bedrock, it tends to follow those bedrock fractures that we've talked about earlier and chase them downward toward where the water table is. And so you get passages that tend to be narrow and very tall. And you can see the person standing in this cave passage for scale. The passage is many times higher than it is wide. In contrast to that, we have what's called a phreatic passage. Phreatic passages are below the water table, so at this point the water's worked its way down to the water table, and now it's starting to flow along that water table or just below it, and so we get oval shaped passages that are often about as wide as they are tall, maybe a little bit wider. These form completely underwater. Now in this case, this is in Mammoth Cave in Kentucky. Obviously, to take the picture in that it's dry. The water table has dropped below this level of the bedrock, and this is now exposed and can be traversed by humans without scuba gear. This is another example in this photo of a cave in central Missouri. And this is the transition from Vados to Phreatic. So I'm the person standing in the picture there. To my back, the passage is much more Vados. It's the part of the passage where the water coming from the surface was working its way vertically down to the water table. And just about where I'm standing is the transition to a more phreatic passage. So if you look forward in the picture in the direction that I'm facing in the picture, you can see that the passage becomes more of that oval shape. So this would have been, when the cave was forming, about where the water table was within this bedrock landscape. And the last thing that I wanted to take a look at inside the cave and today is some of the beautiful cave formations. We're not going to go into depth on how these form. That'll be covered in a different segment. But it's worth taking a look at a couple of pictures here. On the right, we have some big flowstone formations and columns from Carlsbad Caverns in New Mexico. In the upper left, we have gypsum flowers from Mammoth Cave, Kentucky, which is another type of cave formation, actually a fairly rare cave formation, especially in Kentucky or Missouri. You don't see gypsum flowers very often. And in the center there are some small stalactites, which are called soda straws because they're hollow in the middle. And although you shouldn't do this, it would be very unethical and not very good cave conservation. If you broke one of those off because they're hollow, you could use it like a straw to drink a milkshake or a drink or something, hence the name. And we'll take a look at the downstream most end of this diagram and what we might call the most mature part of our karst topography. This is what happens in some what happens and has been preserved in some parts of the world when most of the limestone's been dissolved away and all that's left are sort of the the small pillars, or in this case quite big pillars of undissolved limestone. The valleys here, the spaces between these pillars, are where there used to be caves and used to be limestone, and it's all been dissolved away. Now there's still some small remnant caves in these pillars. This is along the Li River in southern China, one of the most famous karst areas in the world. This is called cockpit or tower karst, depending on exactly how it's formed and the types of towers or columns that are there. And I'll just note that if you watch, there's a lot of movies, several James Bond flicks, a lot of other movies. They've shot some scenery in this part of Southeast Asia and southern China, Thailand, Cambodia that is famous for this sort of tower karst topography that's quite beautiful. And so it's something you've seen but maybe didn't realize what it was before. And with that, we'll end this segment. And in the next segment, we'll talk about karst geography.